In this video lecture, we're going to talk about arrays. We'll first start by addressing the foundational concepts of arrays, then we'll move on to seeing how we can implement arrays in our programming environment, Visual Logic. Let's review the concept of a variable. A variable is a named location in memory. We use variables to hold on to values in our programs. We know one of the traits of a variable is that it can only hold a single value at a time. And if we try to store a new value in a variable, the previous value is overwritten. So what happens if we want to do something like store 100 items? Well, that gets to be cumbersome very quickly because we would need 100 variables to store those 100 different items. Makes me want to scream thinking about it. But if those items are somehow related, we might be able to come up with some type of structure that would allow us to store all of these related values without having to deal with the overhead of 100 variables. And this is where arrays come into play. An array is going to allow us to store multiple values using only a single namespace. So we'll be able to have a single name, and under that single name, we'll be able to store multiple values. The way that this works is we're going to be able to access the individual items that are stored under that single name by using an index number. In other words, we'll say this is the name of the variable location and I want the item at number 1 or number 2 or number 3 at that named location. So we're going to use indexes to kind of help expand what it means for a variable to hold on to something. And this is very similar to if you've ever written a list down on a piece of paper. You are already familiar with arrays. So let's look at an example list. This is called my to-do list, and my to-do list has 3 items in it. And so you'll note that my to-do list has a name. And you'll notice that there are 3 items stored on my list, and each one of them has an index number. So at index number 1, I can see that there is get milk. So on my to-do list, at index 1 is get milk. On my to-do list at index 2 is exercise. On my to-do list at index 3 is do homework. So since all of these items are related to items that I should be doing, in other words, there is a logical grouping of these items here, these strings indicate what it is I should be doing, it makes sense to loop them or group them under a single name that is a way of labeling what those values represent. We can have more than one list. So let's take a look at a quick photograph or two that I've created. Here's another to-do list that I went ahead and wrote down on paper. And you'll notice that at the top there is a name to this list. Again, it's my to-do list. I've got stuff I have to get done. And you'll note that first I need to mow the lawn, then I have to do some laundry, and then I have to run. So if I said to you, what is the third thing on your to-do list? You would say, run. But it's possible in life that we have more than one list of things to do. I know I do. So here are 2 lists. In addition to my to-do items, I have a grocery list. And I have a list of things that I need to get while I'm at the food store. And if I said to you, hey, on your grocery list, what is the third item? You would say bread, right? Because at number 3 on my groceries list is bread. So notice that the groceries list is named groceries and groups together a number of food items I need to buy at the store. And my to-do item is named to-do and groups together a number of activities that I need to perform. And we're going to be doing this within the computer. This is the concept. You've already worked with lists. You're used to working with named lists. All arrays is a way for us to take this concept of using a named and numbered list of items and transpose that into the computer and use that in creative ways to solve computational problems. So let's talk about some terms related to arrays. So an element is going to be a value stored in the array. So in my to-do list, I had the item mow lawn. So one of the items, one of the elements in my to-do list is to the string that has the characters in it that spell out the words mow lawn. So any element in our list, we will use the term element. So a thing stored in our list is going to be an element, a single item. Next up is going to be the upper bound. We know that we do not have infinitely sized lists. On my paper written lists, the size of my list is limited by the size of the paper. In other words, depending on the size of my handwriting and the size of the paper, there is an upper bound or an upper limit on how much stuff I can write on my list. I know I've got some to-do lists that are pretty long, but again, they're limited by the size of the paper that they're written on. So the upper bound is going to be the amount of memory or the amount of space, the maximum amount of space that we have allocated to our list. And so that'll be indicated by the largest index of the element in the array. Lower bound, one of the things you're going to note as we move forward is that all arrays actually start with the index 0. One of the good things I often tell students is, you're starting to get programming and CS concepts when a friend asks you, hey, how many people are out for dinner? How many people do we need for our reservation? And instead of saying 1, 2, 3, 4, they go 0, 1, 2, 3. Oops, I made a mistake. Once you start counting at 0, you know that some of these CS concepts are starting to permeate into your brain. So the upper bound, the largest index that our list provides. The lower bound will always be 0. It's the first index in our list. And every list is going to have a size or length, and that will be the total number of items the array can hold. In other words, how many items can I hold? Can my whole list hold 5 items, 6 items, 7 items? And if we go back and take a look at my to-do list, you will note that my to-do list can hold 3 items, and my grocery list here can hold 5 items. So that's going to be the size or length. And I'll probably use those terms interchangeably for this, because there may be cases where those terms mean something different. But in this case, the length of our list or the size of our list is going to indicate the total number of spaces available to our list. So when we're working in visual logic, we're going to use an intrinsic function to make arrays. And that intrinsic function is called makeArray. And it's going to require 2 parameters. So between the parentheses, we need to do 2 things. We need to provide the name of the list, which will be the first thing. And then after that, we're going to provide the upper bound, or in other words, what is the index of the highest numbered index of items that we can store in our list. So we always have to declare an upper bound because we have a finite amount of RAM, we have a finite amount of computational resources, so it doesn't make sense to actually go ahead and just assume that our list is infinite. Let's talk more about the size or length of a list. When you define the upper bound of an array, the computer will reserve all of that memory in advance for the array. And it's important that you know this because when you think, well, how many items am I going to store in this array? You want to be like a good steward or a good citizen of the computer's resources and not just tie up resources that you don't intend to use. The sample I often tell students is you would never make reservations at a restaurant for 20 people and then only have 2 people show up. You'd be wasting 18 seats, and the restaurant would be very unhappy because they thought they'd make a lot of money and they didn't, and maybe they turned down other reservations. So when we're talking about the size of an array, we want to make sure that we only reserve the number of memory spots that are logical for the specific implementation that we are working on or whatever problem we're trying to solve. So we want to consider what we're going to store in it and try to come up with some guess. Doesn't mean you'll always be right. Sometimes you might need more. Sometimes you could probably get away with less. But as long as we're in the general ballpark, like if you made reservations for 4 people and only 2 showed up because some friends had to cancel, most restaurants can accommodate that. Or if you made a reservation for 4 people and 6 showed up, they could probably pull another table over. So this idea that as long as you're close, most times that's okay. But when you're really far off, that can cause some issues. So just a reminder that reserving space that you don't use takes up space. Here's a different way to visualize an array. I used a spreadsheet to set this up. And one of the things you'll note is that this array is called grades. Notice that now my indexes are going to start at 0. So the first location, or the lower bound of my grades array, is index 0. And notice that there is no value in that location. So array indexes can be empty. There can be no value in it. If I go to index 1, you'll notice that the value stored there is 100. So at index 1, if I said, hey, what's at index 1 in the grades array? You would say 100. Index 2, it is empty. Notice that index 3 has a 93 in it. Index 4 is the number 0 in it. Number 0 is a number. Note that having the number 0 in this specific list is different than having nothing in a location. 0 is something, it's just 0. Another thing to note is that all of the items in a list need to be the same data type. So notice that this list is all integers. Your list either needs to be all integers or all floats or all strings. You can't mix strings and integers or strings and floats. You basically have to have all of the same data types in a list. So what happens when you try to access an index that doesn't exist? If the upper bound of your array is 9, but you try to access index 27, you're going to get an error called an out of bounds error. And basically what that means is you're trying to access an index that doesn't exist. It's like if the highest numbered house on your street is number 9 and you send a pizza to house 27, you're going to have a very angry pizza delivery person. As a former pizza delivery person, I can tell you that is true and happens more than you would think. So this idea of trying to access an index that doesn't exist is an out of bounds error. So we have to be cognizant of what the upper bound of our array is in our program so we can not run into these errors. If I want to ask the computer for a given value at a certain index in a list or in an array, I'm going to use this specific syntax. So in Visual Logic, you give the name of the list, just like you might to a person who's holding on to a list, and the index. So I say, hey, in list grades, what is at index 3? And this is how you say that in Visual Logic. You give the name of the list, followed by a parenthesis, followed by the index number of the item you want, followed by another parenthesis. And we'll see how this is used in a Visual Logic program shortly. So the name of the list, followed by the index. If I would like to change the value at a given index, I provide the name of the list and the index number again, but this time I do so on the left-hand side of an assignment operation. So this would take the value 100 and store it into index 3 of my grades array. If there was already a value there, what would happen to it? It would get overwritten. Individual indexes of an array work just like regular variables. So you can't, if I try to save something over an existing value, that existing value will get deleted and replaced with the new value. So this is how we save or write a value to a given location in an array. For any given array index, if you don't set a value to it, it'll be empty. And one thing I'll point out is that depending on the language you're using, what it means for an array index to be empty is different from language to language, whether you're working with Java or C. And so we'll play around with what this means in Visual Logic as well and see what that means as we move forward. So know that if you don't save a value into an array, there will be nothing there. It'll be empty. And what empty means depends on the language. A couple of general array things to identify as well. Array indexes are always positive integers, so you may have noticed that if the lower bound is 0 and the upper bound is defined by whatever we set it at, note that there are only whole numbered positive integers for array indexes. So there's no index 3.5 or index 3.7. Array indexes are whole numbers and they're always positive starting from 0. And since array indexes are represented by integers, we can also, instead of having to use hard-coded numbers to access an array variable, in my example here, I create a variable called myVariable. I set it to 3, and then note that I can then use that variable to access index 3 of the grades array. So I can set the value at index 3 of the grades array to 100 using a variable, just the same way that I could do so using a hard-coded number 3. And this is really interesting because if we can use variables to represent array indexes, and we know that array indexes are whole numbers, that means we have a way to work through all items in a list. And we do that using arrays and for loops. They are used together a lot. So for loops let us perform repetitive tasks, and arrays since arrays let us store a lot of information, the repetitive task that we may first want to perform is, hey, print out all of the items in this list. So for every item in this list, print it out. Start at index 0, then go to index 1, then go to index 2, then go to index 3, and each time you visit a new index, print something out. We've already looked at how to write for loops that count up by 1. So our initial value would be 0, our final value would be the upper bound of the array, and we would increment by 1, getting from 0 to the upper bound. And in doing so, we could use that loop control value to essentially be the value that we use to access a given index of an array. One final thing that we'll talk about is this concept of parallel arrays. What's a parallel array? Well, if one array is good, two array is, well, twice as good, I guess. I don't know. But sometimes, an array can hold a given value at an index, and sometimes it makes sense to have two arrays. And we'll see this in the book in terms of having two arrays, where one array holds a list of usernames, And another array holds a list of passwords. And what we're going to do is come up with this rule that anything at a given index number in one array is tied to a given index in another array. So the username at index 0 is associated with the password at index 0 in the password array. So let's take a look at an example of how this works. So here's my example. Username 0 is Jason1. So my username is Jason1. And that would mean that in the other array, the second array named password at index 0 is the value 1234, and that would be my password. So these two arrays contain separate information. The username array only contains usernames, and the password array only contains passwords. But we use the index as kind of a key. So if you're familiar with databases, it's the key that ties the two lists together. This idea that my user index, or maybe even we would probably consider it my username at index 0 is the same as the password at index 0. One of the obvious problems that can arise with parallel arrays is they can get out of sync. What if there's a mistake and a programmer thinks, instead of accessing index 0 in the username password array, they access index 1, right? But this idea that we can have two separate sets of information that are tied together via an index is the concept of parallel arrays. So it sounds a lot more complicated than it is, but this idea of, you could even think about it again if you have database experience where you have two separate tables in a database, and the index is the key that ties those two items together. All right, let's move on and take a look at how all this can work in Visual Logic, because it's great to talk about these things conceptually, but they really come together when we start to look at them in code.